The topic for the lecture today is induction on terms and induction on predicates. So let's first talk about induction on terms. And the question is, why do we need induction on terms? And to see why, let's consider this problem. We'd like to show that for every natural number x, we want to show that a of x is true. Because we don't have any way to apply induction at the moment, in order to prove this property, we have to show that a0 is true, a successor of 0 is true, a successor of 0 is true, and so on and on. And this is clearly infeasible because there are just infinitely many natural numbers. So we needed to have some way of applying induction, just like we prove the same statement in mathematics by applying mathematical induction. So the plan now is we'd like to derive on another elimination rule. So we have the introduction rule for this judgment. So we have an introduction rule for this judgment for data type NAT. So we have introduction rules. And the plan is we'd like to derive an elimination rule which allowed us to apply induction on terms directly. With this elimination rule, we can show that we can prove this property. So let's use this data type NAT as a running example. Remember that the goal is we'd like to prove something like whenever we have a judgment like this, we can show that A of n is true. And we'd like to prove this statement by applying induction on this judgment or this term n. So we have two introduction rules for this judgment. The first is 0 belongs to data type NAT, and this is NAT introduction rule 0. And we have another introduction rule, successor t belongs to data type NAT if term t belongs to data type NAT. This is natural number introduction rule successor case. So we have these two introduction rules. Now we'd like to derive an elimination rule that allows us to apply induction on terms of data type NAT directly. So suppose that we have this judgment term t belongs to data type NAT, and we'd like to somehow show that A of t is true. And so there are two ways to complete the proof of this judgment. First, by applying this introduction rule, and second, by applying this introduction rule. So now we are going to have two cases to analyze. The first case to analyze is the last inference rule applied to the judgment. To the proof of this judgment is this introduction rule. But the first case is t is actually equal to 0. So in this case, we have to give a direct proof of A of 0 true, because we want to show that A of t is true. So that's the first case. And in the second case, the last inference rule that was applied to the derivation tree of this judgment is this introduction rule. So we can imagine that T is actually successor of something, and we don't know what this something is. So let's rewrite this one as x. So we have something like this, where successor x is equal to term t. Now the goal is we have to show that a of successor x is true. And the hypothesis is, first, we invert this introduction rule. So we know that this judgment is true, and we know that this judgment was proven by applying this introduction rule. So we automatically have a proof of this smaller judgment. So we may use this judgment as hypothesis because we know that it's true. And now here's the critical part. Our goal is to show that whenever we have this judgment, we would like to show that this property holds. Now, thinking inductively, we have a smaller judgment. To be precise, we have to say that the size of the proof of this judgment is smaller than this one. So if we imagine a derivation tree, then the derivation tree for this judgment is smaller. And currently, we are talking about the property of this judgment. So if we think inductively, we may assume that the same conclusion can be drawn from this smaller judgment. So you have to think inductively, or you want to recall the principle of mathematical induction. That is, we are trying to establish a property from this judgment, and its proof is strictly larger than the proof of this smaller judgment. So we want to introduce a hypothesis from this smaller judgment. So we introduce a hypothesis from this smaller judgment. And in this case, it is A of x true. In the course of proving this judgment, you may use these two hypotheses. This one, which simply says that this is well-formed. This is well-formed. That is, x is a natural number, and A of x is true. And this is justified by the principle of mathematical induction. So by combining these two, you somehow complete the proof of this judgment. And we have to assign a label here. And we'd like to use label u of x. And the reason that this label includes a variable x is the proof of a of x depends on term variable x. So to indicate the dependency, we'd like to use this variable u of x. And then whichever introduction rule was applied to the proof of this judgment, we can always deduce this judgment or this judgment. That is, we can show that A of t is always true. So this is a new elimination rule, natural number elimination rule based on induction, and we introduce new variable u of x. So we can assign this name to the disinference rule. So if we think about this elimination rule, the first case corresponds to the base case in mathematical induction, and this one corresponds to the inductive case in mathematical induction. And this term t is just a concrete term for which we'd like to establish a property. And typically, this term t is a variable. For example, this could be variable x, or another variable y. In this case, this one is called induction variable. So this is new elimination rule. And to summarize, the motivation for introducing this new form of elimination rule is we'd like to prove a property of a term of a specific data type. And the requirement here is you have to provide introduction rules for this judgment. So in other words, whenever this data type is introduced inductively using introduction rules based on natural deduction, you can derive a corresponding elimination rule, which allows us to prove this one. So let me summarize this one. So the inference rule reads term t belongs to term t belongs to data type net, and we would like it to show that a of t is true. And in order to show this, you have to consider two cases. First, a of 0 is true, and the inductive case is you have to show a of successor x is true, where we assume that t is a successor of x. And you can use the two hypotheses. The first is x is of course natural number, and you have a of x is true as hypothesis. And let's use the term variable u of x. And then the inference rule is called natural number elimination rule based on induction using variable u of x. Now we'd like to assign a suitable form of proof terms. And so let's do this exercise. So this part is easy. Let's assume that there is a proof term n of type A0. So we use this principle of Curry-Hall isomorphism interchangeably. But depending on the context, we may interpret this one as proposition, or we may interpret this one as a type. And here we interpret it as a type. So we have a proof term m of type A0. And here we use this variable u of x. So now the variable of type a of x is u of x. So now this label is gone. And using this variable, term variable x, an ordinary variable u of x of type a of x, assume that we can find a proof term n. So of course, this proof term n may have references to this term variable x and this ordinary variable u of x. Now the question is, what kind of a proof term would you like to assign to the conclusion here? So this proof term would have a type a of t. So any form of a proof term is fine as long as it contains this term t, this proof term m, and this proof term n, and this variable x, and this variable u of x. Of course, the use of this term variable x and this variable u of x is optional inside n. So essentially, this proof term should contain these three elements. So you may choose any form of proof term, but we'd like to interpret it as building a function. So what we are, so imagine that you are building a function or this black box, which takes a term of data type nat. So it's going to be, so this is the input to this function. And this function is going to return a proof that a of t is true, or equivalently, it returns a proof term, some proof term of type a of t. And we'd like to call this function new, or you could call it induction function. So imagine that we are building this induction function new, which takes term t and returns u of t of type a of t. With this idea in mind, now we can choose a suitable form of proof term here. So we use the keyword in to indicate that we are in the middle of applying induction. So we want to create u of t, and there are two cases. So we are performing some sort of pattern matching here. If this one matches with u of 0, in which case t is actually 0, we take this proof term m. Otherwise, we have u of successor of x, in which case we take this proof term n. So that's the new form of proof term that we'd like to assign to this elimination rule. So remember that inside this proof term n, you may use references to this term variable x, as well as this ordinary variable u of x. So this is a new form of proof term. Now the set of proof terms is expanded with a new form. Induction u of t of, if this is u of 0, then you calculate m, or if this is u of a successor of x, you calculate this proof term n. So this is a new form of proof term. And it turns out that because we have this new elimination rule, we can even think about beta reduction. So let's work directly in terms of proof terms to see how this beta reduction works. Remember that beta reduction is all about eliminating detour, and detour is intro immediately followed by elimination rule. So let's directly work with the proof terms. The first form of introduction rule is just 0. Natural number 0, and then this is the elimination rule. So what I mean is this proof term comes from the elimination rule. So this is introduction rule, and now let's build a proof term from the elimination rule. So which is induction u of 0 of u0 m, or u successor x n. So in this case, we simply take the first branch. So by applying beta reduction, you obtain n. That's all. What about the inductive case? Inductive case looks like instead of 0, you have this one. This is the second form of introduction rule. So the second form of introduction rule looks like if t is a natural number, then successor t is also natural number. This is a natural number introduction rule, successor case. So this is what you obtain after applying this introduction rule. So this is intro, and this corresponds to the elimination rule. So let's build a detour by applying this introduction rule. So now you have successor t, and then let's introduce this elimination form, u of successor of t. If this is u0, then you take n, and if this is u of successor of x, you take n. And remember that inside this proof term n, you may have references to term variable x, and as well as ordinary variable u of x. How do we better reduce the whole proof term? So the first branch doesn't work, doesn't match. So we take the second branch. Now the question is, how do we expand these two variables? So this term variable x is, of course, term t, which is contained here. So this corresponds to x. Now what about u of x? So remember that this function, induction function u, takes a particular term of data type net and returns a proof term u of t of data type a of actually a proof term of type a of t. So now you have to show that now you have to find a proof term which should have type a of t, and that's precisely what this elimination form provides, with a minor difference that the term is now t instead of successor of t. So the plan is you make a copy of this whole proof term and use just the t instead of successor t. So you copy this one, induction u of t. So notice that now we use t instead of successor of t. And you just copy the whole remaining part. It's u successor x of n. And you will use this proof term for this variable u of x. So that's the second part of beta reduction. And for this particular case, we don't have actually eta expansion because judgment is about term and data type. But the conclusion in this elimination rule is about proof term of type, not data type. So this is the proposition or type, not data type. So we have two heterogeneous forms of judgment, this one and this one. So they are incompatible. And that's the reason that we don't have actually eta expansion here. Now let's look at a simple example. So we'd like to prove that for every natural number x, there exists natural number y. So natural number y such that x is less than y is true. So we'd like to prove this judgment. So this is less than predicate that we have defined in the previous lecture. And the course notes provides the complete derivation tree, but here I'd like to just highlight the key idea. So we have an instance of this existential quantification. And because we are dealing with the constructive logic, in order to prove this judgment, you have to actually find a concrete witness for this term variable y. And in this particular case, it's pretty easy to find such a witness. So for example, for every natural number x, we could choose successor of x as the concrete witness, because we know that successor x is always greater than x. Then the whole problem reduced to showing that for every natural number x, x is less than successor of x. So if we can prove this judgment, it actually conveys the essence of the proof of this original judgment. So instead of proving this judgment, let's try to prove this judgment. And the judgment here complies with the pattern that the previous elimination rule, the new elimination rule, intended to target. So it has something like some term has some data type, say tau, in this case net, and we'd like to show that this term t satisfies this property A. But this judgment has this form, so we can use the new elimination rule for data type net. It's pretty easy to complete the derivation tree. Let's just say instead of this one x, let's just say this one is n. For every natural number n is less than successor of n. So how do we prove this? Let's say this is a of n, okay? Then this one is so to prove this, assume that n is a natural number, so we have this judgment. And now we have to show that a of n is true, which is n is less than successor n is true. The first case is n is 0, and the second case is n is successor of x for some natural number x. So essentially, we are actually performing mathematical induction, but using our notation in this constructive logic. So you have to show that a of 0 is true, and this is basically 0 is less than successor 0 is true. So you have to show this one. But there is an introduction rule that matches with this conclusion. So this is less than introduction rule 0 case. And in the inductive case, we have to show that a of successor x is true, and the hypothesis is x is a natural number, and the second hypothesis is a of x is true. So this can be called, for example, u of x. Now let me expand this a of x and a of a successor of x. So this one expands to x is smaller than successor of x is true. And this one expanded to successor x is less than successor of x is true. And we can easily bridge the gap between this hypothesis and this conclusion by applying the second introduction rule. less than introduction successor. So if you apply this inference rule to this judgment, you immediately obtain this one. So that's the whole proof. So the proof is quite straightforward, and the point here is that now we can apply what essentially amounts to mathematical induction, the principle of mathematical induction, using elimination rule for data type net, for example. So that's the whole key point. Now let's move on to induction on predicates. So the previous elimination rule, which deals with induction on terms, deals with this pattern. So whenever you have something like n belongs to data type net, and I would like to show that a of n is true. So you start with a judgment of this form, or just a term of a specific data type. So whenever you have a term of a specific data type, you'd like to show that this term satisfies this property. And if this judgment is defined inductively using introduction rules, intro rules, you can prove this one by applying the corresponding elimination rule based on induction. So that's the what induction on terms is about. In contrast, this induction on predicates assumes a different situation. This time, we have a proof term, a term of a data type net, for example, and we know that this term n satisfies a particular predicate. So we see the difference between this case and this case. In the first case, we only have this judgment. We have just a term of a specific data type. But this time, we have a term of specific data type, and also we have a judgment, a truth judgment. And suppose that this predicate P is defined inductively. So this predicate P is defined inductively using natural deduction style. So what we are saying here is essentially we have introduction rules. Introduction rules for this predicate P. And then we'd like to show that this N satisfies a predicate a property A. And this A can be any predicate, like a composition of many logical connectives, etc. But the assumption, the requirement here is this predicate P must be defined using introduction rules. And this is the problem that we'd like to solve, we'd like to deal with. So there is a clear difference between the first case and this case. And our intuition tells us that the elimination rule, the second form of elimination rule, will be much more powerful because it directly works with these judgments. So to show the idea, let's consider an example. We want to use this predicate natural number equality, which is defined inductively with these two introduction rules. First, 0 is equal to itself. This is true. This is natural number equality introduction rule 0 case. And the second one is successor m is equal to successor n if m is equal to n. If this is the case, then we apply this natural number equality introduction rule successor case. So we have these two introduction rules. Now suppose that we have two terms, two natural numbers, m0 and n0, and we have this judgment. And we'd like to show that whenever two terms n0 and n0 satisfies this judgment, we will prove that A of nn is true. And this predicate can be quite complicated. It can be any arbitrary predicate that involves this m0 and n0. So let's try to derive an elimination rule. Again, the essence of this new elimination rule is mathematical induction, where we can make a hypothesis for something smaller when we are trying to prove a property of something larger. So let's start with this one. So we have a proof of n0 equals to n0. And now we'd like to show that these two terms satisfies this property A. So there are two ways to prove this judgment, by applying the first introduction rule and by applying the second introduction rule. If this introduction rule was applied, then we would have this is m0, this is n0. So therefore, it suffices to prove A of 0 and 0 true. That's all we need, because m0 is actually 0 and n0 is actually 0. So the first case is gone. What about the second case? In this case, m0 is equal to successor of m, and n0 is equal to successor of n, because that's the second way, the remaining way of completing the proof of this judgment. So the last inference rule in the derivation tree of this judgment would be this one. Now, eventually we have to show that A of successor m, successor n true. And the question is, what kinds of hypotheses can we introduce here? And first, we know that these two terms m and n are all natural numbers. Suppose m, n are natural numbers. Next, we know that this is true because the assumption is the last inference rule in the proof of this judgment is this one. So we have a derivation tree that proves this one. So we automatically have proof of this judgment as well. So we might have to use the fact that m is equal to n. And let's assign label w here. So this hypothesis comes from this judgment, the premise of this inference rule. Finally, we can introduce an induction hypothesis. So we are trying to prove, in a certain sense, we are currently trying to prove a property of this judgment. this judgment. But according to the way that the derivation tree here is constructed, we have a proof of something smaller, precisely of the same form. So by applying the principle of a natural mathematical induction, we may assume that this judgment also satisfies the property A. So that's the whole idea behind the mathematical induction. So the last hypothesis here is this judgment also satisfies A. So you may assume that A, M, N is also true. And we can assign U a new variable parameterized with both M and N. Now the question is, how do we prove this judgment by exploiting these four hypotheses? And that's the natural number equality elimination rule based on induction. So this is the elimination rule based on induction for this particular predicate. And it's actually pretty easy to so I guess this example, this example is enough for demonstrating the idea of new form of elimination rule. Let's go over another elimination rule quickly. So this time, let's consider this less than predicate. So the two introduction rules, 0 is less than successor n. So this is true. This is less than equality introduction rule, 0 case. And the second one is if m is less than n, then successor n is less than successor n. This is also true. This is less than introduction successor case. And what about the elimination, the new form of elimination rule? Suppose the m0 is less than n0. This is true. Then we'd like to show that a m0 n0 true for some predicate a. And this is the first case. In the first case, m0 is equal to 0, and n0 is the successor of n, where n is a natural number. So the hypothesis is n is a natural number, and you are supposed to show that a 0 successor n is true. So you have to build this proof directly. And in the inductive case, m0 is equal to successor of m, and n0 is equal to successor of n. Now you have to show that a of m0 n0 true, but n0 is successor of m, and n0 is successor of n. And first, we know that m is a natural number. Also, n is natural number. And we know that this is true. So we can make a copy over here. So new hypothesis is m0 is less than, m is less than n. This is true. This is new hypothesis. And finally, the induction case is, here we have a judgment whose proof is strictly smaller than this derivation tree. So you may assume that a of m n true. So we can call it u m n. So in the course of proving this judgment, you are permitted to use all these 4 hypotheses. So this is another example of deriving an elimination rule based on induction. So this is less than elimination rule based on induction, where we use 2 variables w and u and n.